can't believe this. I overshot by 1/1000th of an inch. Oh my god. So now that I've turned down to establish a shoulder for the bearings, and I've made 3 marks, as you can see, so that'll be the end of that. This is going to be the shoulder for that nut, and the end of the bearing journal, and this is where the taper is going to start, go to the end. This portion is the bearing journal, and it needs to meet critical measurements, tolerances, and those are, as you can see here, we're going to be between 944,004/10 to 7 to meet the high precision standards that are established in the machinery's handbook. So this is the most, other than concentricity at the lengthwise, this is the most important part that I have to make on this shaft. And so it's been 3 days since I worked on this spindle because I wanted to quadruple verify all my measurements and whatnot. And so now I'm ready to start. Okay, so now I've turned the bearing journal, and this is the front, right? This was extremely difficult. I mean, the tolerance is 4/10 of 1/1000th of an inch. So I had to have it between 984,000 and 3/10 to 7/10 approximately, right? To fall in the category that I wanted in the machinery's handbook. So let's measure this out. I'll show you my measurements. So this is the first measurement, 98485. So that's in hundredths of 1/1000s, right? So I had to go 9847. So 1.5 is good enough for this kid. All right, so let's shoot in the middle and see what's going on there. 98440, again, within tolerance. Last one. Okay, so this one is 98465. So tolerance again from 3 to 7. So 6.5 is more than great. Very happy. Okay, so we established this was my critical dimension that I needed to achieve for the bearing journal. This is that shoulder that nut is going to sit against and provide preload, axial preload, I should say, on the outside diameter of the bearings going in that direction. So now, and I've turned this down already to a diameter of 870,000ths of an inch. Now, the critical time now is to make the taper, which is 7.125 degrees. Now, for best results, I'd want to keep my live center in, which means I need to have my compound going in this direction. So I may have to move my steady rest back a bit in order to clear the compound. So now I have to decide, how am I going to set my compound angle? There's different ways to do that. I could remove this whole assembly from there, but that would be counterproductive because lining this up is difficult. So I think perhaps using a compass would probably be best. So let's go to the bench for a second. All right, so I've got this set up here. This is the original spindle, and I've established that this is okay. Now, what I've got is one of these, and it's quite precise, right? So it's a Brown & Sharp, it's a good tool. So basically what I did is I set up so that I could be approximately in the middle of the tool, of the spindle, pardon me. and then I've set my angle. Okay, so voila, I've got that. All right, so what we have to look for is where that 0 line from here, this dial, goes on. And if you actually have a real close look, it lands on the 7.1 approximately, but I know it's 7.125 because I've leaned it against the actual taper. So now I need to transfer this to my compound, and Bob's our uncle. Well, that'll be fun. Let's do it. Okay, so here's how I'm going to do. I've done this actually. Usually common practice would say, okay, you take your test indicator, a really precise one, and you put your whatever it is the taper is going to be, and you angle your compound accordingly until it's precisely where it needs to be. But I'm unable to do this in this case because I don't want to take the bar out of my lathe. So what I've come up with is using this compass and lining everything up. So I've got some precise angle blocks underneath to support my compass. I've got the cross feed so that everything lines up against this face at the bottom and against my compass. So I've set up a light so that I could see whether there's light against my straight edge or between my straight edge and these two things. So let's zoom in. All right, so what I've done is I've put my straight edge against this, and you hold this to make sure you don't mess things up, and there is no light at all on either side. Now I've tested this multiple times to make sure I was correct, and so that's how I've decided to do this. Now this is certainly not as precise as a test indicator, but it's going to have to do. And the proof's in the pudding. If my taper fits the grinder wheel assembly, then I'm good, right? So I'm going with this, and now it's time to turn that taper. All right, my compound is set up. Now, before I get started, it's really important to make sure I got my stuff together, right? I've got a tool that's going to fit inside that space all the way. I've also determined that, my compound has enough travel to come all the way back to where my mark is or further, right? So that's good as well. So what I need to do next, oh, and by the way, I wasn't able to keep my steady rest in place, but that shouldn't be an issue. All the pressure is going to be here. I'm going to take very light cut until I get to where I need to be. So at most 20 thousandths of an inch cuts. I'm going to lock my saddle in place, and I guess it's time to take a deep breath and go for it. First thing I'm going to do is put an idiot mark on the shaft where I need to stop. So here we go. Little bit at a time. By the way, on my left side I've got that chuck turning, so gotta be careful here. If you're gonna do this, be careful. At this point, I'm going to start cutting from the shaft part only. Don't want to miss the mark. I'll do spring passes every time on the way back. Getting very close here. Next pass probably going to be just a couple of thousandths instead of 5. I'm really not liking this finish, but hey, I did say I was going to use a different tool, so perhaps this is the time to do that. My different tool in. Now it's time to give her a shot for the last pass or so. That's it. Now the test, right? Oh yeah, it's pretty rough. Well, I'll take some memory cloth to this thing here in a minute and deal with that. Okay, so I'm done the taper. Time to even up the surface and make it a little shiny and whatnot. So let's do that. Sorry, I'm right-handed, so you're going to be on the wrong side of things. Use a softer grit, give it a better finish. That, my friends, should do the trick. Doesn't need to be extremely polished here. As long as the angle's correct, that's all I need. So now, another moment of truth. I would have to withdraw my tailstock and bring in something to test that taper. Alright, so every time you try something, you gotta wonder yourself, did I mess this up? Did I do it right? So, here it is. That's my spacer. So, oh yeah. No movement. Zero. Zip. This is exactly what I was hoping for. So, I'm very pleased. Time to grab some lunch and come back and re-strategize. Woohoo! While I'm on the topic of drilling in order to tap, because this is pretty mission critical, I'm using 4140, which is a medium hardness steel. But nevertheless, the harder you go, and the harder the metal is, and then of course your tap might have a bit of an issue with what you're about to make it do. So I'm drilling for a 3/8/16. And there's, as you can see here, 60% and 75%. And what does that 60% and 75% mean? Well, that means we're going to leave 75% of the material required, and this is 60, so this is going to be a little bit looser. Unless you need something super tight, just pick 60. And then, okay, we see here 3/16, there it is. Move across and it tells you 21/64 for the 60%. So that's a very important thing to know, right? Just FYI. Gonna need lots of oil, so put that here right now. Okay, here it comes. I'm going to follow the 1 and 3 rules here. This is 4140. I don't want to mess around. If you go in there too fast, it could harden on me and then really cause some bit breakage. So I'm going to keep going until it's time to tap. Before I go right into tapping, I've decided to put a 60-degree chamfer in there. I just at the entrance of the hole clearly, and that is because if I want to use a live center again at the other end, put them between two centers, I'll be able to do that, or for future uses. So that's what I'm going to do now. Don't need a lot. Yeah, that's right. The other advantage to doing this is that now my tap's going to go in there really easily, and it won't be a fight to do that. So let me get a tap full ore. Alright, I've got my tap set up, tap full ore behind it. It's spring loaded, so it's going to help me push that and keep it nice and straight, which is always a good thing. So we should keep that clean, lots of oil, and here we go. I could use the motor, but I would rather not. Okay, that, my friends, is enough. Okay, I thought this might be a good time to go over some of the features on my new spindle and explain why I made the modifications. This is the new one here. Of course, I just took it out of the lathe temporarily. And this is the old one. As you can see, this shoulder is much closer to the end of the spindle, and have added a shoulder for the bearings to sit against. The bearing journal is much shorter. In fact, the bearings actually go from here to here. This is the end of it right there. And then that nut, this one, that goes in here, right, will actually go up to here, the end of this line here. The reason for that is I'm allowing for axial preload. To create preload, you gotta have something sitting here, that'll be the shoulder, and then something pushing against here, and that'll be that nut, right? This part here on the outside. And that way, what happens that, sorry, wrong finger, but the bearing actually goes like this. There's room inside, right? There's some flex. And by pushing the two axes one against the other, it creates preload against the ball bearings that sit against like there's like a raceway inside. So it makes them a little tighter, it runs tighter. The same thing is true about what's called radial preload, which is preload made by a shaft that is of a larger diameter than the inside diameter of this bearing. That way it pushes, let me see if I can reach over there, it pushes outward, right? Again, creating some preload on the outside, because this here, the outside of the bearing is sitting against the sleeve. So, and there are bearings such as these ones that can handle both in order to produce higher precision by tightening the bearings that are on the inside of all this. So because I'm making this spindle for a surface grinder, which requires high precision, I read all of the documentation from SKF regarding the tolerances that this bearing can take and how it can perform given a certain amount of preload that is applied onto it. And with that documentation and what I read on Machinery's Handbook, I was able to come up with the sizes that I've been using. So if you're curious about what preload is, now you know. It took me a fair bit of reading to, decipher all that stuff because I'm new at this. but it's well worth reading if you... Okay, I might as well show you this. Of course, the material that I've used for creating the new shaft was 24 inches long. The original shaft is 18.5 inches. When I started the project, I was working at that end over here, and I overshot the bearing journal by 1/1000th of an inch. So I ended up being too small. So what I did is I flipped it around, created this. It gave me a chance to practice, so that's okay. And so now this is all done on this end, and I can go over here. So I'm gonna measure 18.5 from here to there, cut the shaft, and then put that back in the 4-jaw chuck, get everything trued up, and perform the various operations that need to be done here in order to get what's over here, which is the back end. That's the pulley end. This is the other bearing journal for the back bearing, and then some threads which are of equal diameter to this bearing journal. That should be a whole lot of fun. Here we go. Okay, I'm about to go into combat with this thing. So I've been saying 18.5. It's actually not 18.5. The whole shaft is actually 17 and 15/16. I was giving myself extra room to wiggle with. So this here marks the location where I could put my 4-jaw chuck for concentricity aspects, but I think I'm going to put it there just to be safe, you know, and then it's going to make this shorter and of course sturdier, which is a good thing. All right, so what I've done is I've measured all of this out, and I need to make 17 and 15/16. I need to phase this up to this line. So then the features that I need to make are nominal, except for the bearing journal, which is this, right? So everything else, there are things that are missing. For example, this is too wide for the bearing, and it should have a shoulder, so I'm going to add a shoulder to my design. This I need to make in order to get into that space in the housing, and the rest is nominal. Which nominal meaning, you know, doesn't have to be super precise. Okay, so here's the design. The little S here means, you know, I'm chopped out a particular length of material. And what I've done is, once this is trimmed to 17, 15/16, the measurements that are, you know, for each of these things here, I've given myself targets by drawing this little diagram. It just makes things easy, because the first thing I'm going to do after everything is lined up and concentric, I'm going to turn down and reach here. That's to clear the housing on the inside. Then I'm going to go and create this shoulder for the bearing inner diameter ring. Then this is the critical bearing journal. This thread is actually the same diameter as the journal, so that should be interesting. And I might practice beforehand, or I'm not sure. Unfortunately, this is not a standard thread. It was custom made, and because this pulley journal diameter, I don't have much choice but to recreate this thread pattern. So, and of course then there's this, which is, you know, to my discretion, but the diameter is not. Okay, so that is how I'm approaching this. So here are my calculations, should you be interested. And now it's to delay to put this in there and line things up. Okay, so This is completely cool now. It's just been like 15 minutes. Okay, so I'm taking my measurements again. Go as close as I can to the shoulder, because that's where the bearing's going to sit. I'm at 672.45. Okay, so I had 22.95 thousandths to go. I just took a 15 thousandths cut, and so that should leave me 7.9 thousandths of an inch. So we'll see. I'm making sure the shaft doesn't get too hot. It's, see, just warm enough I can still touch it, because I don't want false readings. Okay, so this here is indicating right on the money. So you can see that here. Okay, so my final target is 670 thousandths. I've got 7.6. I thought 7.9. So I'm on target. Now I'm going to. This is where it gets a little rough. So either cut, probably 5. I'm going to cut 5 thousandths of an inch, and the rest will be emery cloth. And I'm going to subtract 1 just to be safe. I don't want to mess things up. I'd rather have more and cut more later than not enough, right? So okay. This is time to be really meticulous. There we go. I'm cutting 4 thousandths. Okay, my dial was at 184. I'm going to put it back there. Okay, now this is going to take time. Not the most outstanding finish here, but that's okay. When you take really light cuts like that with carbide tip, it's not always wonderful. That's okay. So take a quick measurement. Wow, right on target. Okay, so I'm at 672 thousandths and 1/10, 1.5 tenths. Perfectly acceptable. So now what I'm going to do is let this cool down completely, and then it'll be emery cloth time. So I'll bring you back. Before I use the emery cloth, bring this down 2 thousandths of an inch, actually 2.45. This is where the bearing is going to sit. So that'll be the journal, and this is all I really truly need to polish down, right? From here to here, about 5/8 of an inch is going to be threads, and they're going to be the same diameter as this. So I can go over this, there's not an issue at all, and then this is going to get taken down for the pulley. So with no further ado, here's what I'm going to do. I'm going to use some 400 grit emery cloth, and then when I get close to my target, I'm going to use 600 grit just to give it that final polish. So at this point, it's very important to take my time.